Hey everyone, so we're looking at section 5.1 today. As you can see, we will be talking about discrete probability distributions. Of course, we do want to start out with what a probability distribution is and then get a little bit more detailed into this. Now, specifically, we will be concentrating on the binomial distribution, but obviously, as you can see, there are other forms such as multinomial, Poisson, hypergeometric, and geometric as well. So let's start out here with defining some terminology. So remember we had started talking about variables, and as you can see that was in chapter 1. Now that can be defined as a characteristic or an attribute that can assume different values, right? Now of course we know you can use different letters from your alphabet to represent variables. So here we'll talk about a capital X, Y, or Z, or depending on what data you're looking at, you can define your variables based on that. Now here we're saying that since we are going to be talking about these variables in terms of probability, we are going to call them random variables. Okay, so just think about some examples here. We're saying if we are rolling a die, then you can think of the letter X, or the variable X is going to represent the outcomes, right? So when you're talking about rolling a die, your outcomes could be the numbers 1, 2, 3, 4, 5, or 6, right? The numbers that you get when you roll a die. Now, if we are talking about tossing 2 coins, then you can actually think of your variable, let's say Y, that can represent how many heads will you get when you are tossing these 2 coins, right? So you can either get 0 heads because both the coins landed on the tail side, right? You can get 1 head, which means out of the 2 coins, one of the coins landed up on a head, or you can get 2 heads where both your coins ended up on the heads, right? So you can think of, again, the variable Y representing the number of heads, and then the outcome for those values would be 0, 1, or 2. Another example they're talking about is they're saying, okay, if the temperature at 8 a.m. is 43 degrees, at noon it goes up to 53 degrees, then you can say the values of T is going to be the temperature, basically. And in this case, we would of course say your variables are temperature T variable is going to assume random values, since obviously we have no control over that, right? It's going to be based on atmospheric conditions, and in that case, we would say it's going to be a random variable. So just as a definition, we are saying a random variable is a variable whose values are determined by chance, okay? Another thing that we had talked about in chapter 1 was variables that could be described as discrete or continuous. So you should remember that when we were talking about discrete variables, we were saying those were the variables that you had to count to get your values. And of course, continuous were where you had to use a measuring device to get those values, right? So they're saying if a variable can assume only a specific number of values, such as the outcomes from a roll of a die or the outcomes from a toss of a coin, then we would say that is a discrete variable. So your discrete variables can either have a finite number of possible values or an infinite number of values that can be counted. So remember, discrete variables again are the variables that can be counted. We're saying variables that can assume all values in the interval between any 2 given values, we call those continuous variables. So again, continuous variables are obtained from data that can be measured rather than counted. Now, for now, we are actually going to be focusing our attention on discrete random variables. We're not going to worry about continuous ones till we get to the next chapter, okay? Alrighty, now let's talk about, now that we have defined our variables, we've talked about what random variables are, and that we're only using the discrete random variables in this chapter. Now let's get into our probability distribution here. So just as an example, we're talking about constructing a probability distribution based on this probability experiment where we are tossing 3 coins. Okay, so if you're tossing 3 coins, you can get all 3 of them landing up on tails, or you can have 2 tails, 1 head, 2 tails, 1 head, 2 tails, 1 head, but just depending on which coin lands where, right? The other side of that could be you can get 2 heads, 1 tail, 2 heads, 1 tail, or all 3 of them land on a head, right? So all of those outcomes, which of course is a total of 8 outcomes, is what we can get from tossing 3 coins. Now let's say we take our variable x and define it. Of course, remember this is going to be a random variable again, and we define x as the number of heads we can get out of this little experiment. So in this case, your x can assume the values of 0, no heads at all, 1 head, 2 heads, or 3 heads. Okay, so no heads, of course, 0 heads means you're going to have all your coins land on a T, right, on a tail. So that's going to be a probability of 1 out of the 8 outcomes. So that's where we get this probability of 1/8. Now, if we only get 1 head, then those are going to be these outcomes, right? TTH, THT, HTT. So that's again 1 out of 8, 1 out of 8, 1 out of 8. But since there are 3 outcomes like that, that ends up giving us a probability of 3/8. Now, those outcomes where you have 2 heads, again, there's going to be 3 of them. So that will also have a probability of 3/8. And there's only 1 outcome where all 3 of them are going to be heads, right? So this again will have a probability of 1/8. Now, how do we write our probability distribution? So since here we are talking about the number of heads, you are going to put that as your value on the top. So number of heads using that variable x, and then that's 0 heads, 1 head, 2 head, or all 3 heads. And then you put your probability p of x on the bottom row or the second row, and then underneath each outcome you are going to put your probability. So we can get 1 out of 8 outcomes where we have 0 heads, so that's 1/8. 3 out of the 8 outcomes, and again you can kind of see this little table we had here. So 3 out of those 8 outcomes gives us only 1 head, so that's the probability 3/8. Sorry. There are again 3 outcomes which give us 2/8, so that's 3/8 for the 2 heads again, and of course only 1 outcome which gives us all 3 of them to be heads, so that's a probability of 1/8. So you're basically taking your outcomes and seeing how many of those outcomes satisfy our variable, and then based on that you come up with your probability distribution. So again, just as a definition, we're saying a discrete probability distribution consists of the values a random variable can assume and the corresponding probabilities for those values, right? And they are saying these probabilities you can either determine theoretically or by observation. So what we just did here with the 3 heads is what you would obviously call as theoretical probabilities, right? Just your procedure table of constructing your frequency distribution. Of course, the first thing is making your frequency distribution for the outcomes for your variable, then finding the probability of each outcome, and this is of course by dividing your frequency for that outcome by the total of your frequencies, right? And they're saying again, step 3, if a graph is required, you will put your outcomes on the x-axis, probabilities on the y-axis, and draw vertical bars for basically each outcome, right? Kind of like we did with our bar graph, or you can even think of histograms. You're using that same concept here. Okay, so again, you can either use graph or a table to show your probability distributions here. And let's take a look at this first example. So we're just using a simple example of rolling a single die. So we know those outcomes will go from anywhere from 1 through 6, right? Now, rolling a single die, remember, is your classical probability. So we know each outcome will have the same probability of 1/6. So your outcome x, we're just using x as our variable, are going to be the numbers 1, 2, 3, 4, 5, and 6. And then, of course, like we said, each of them will have the same probability. So that's the probability of 1/6, 1/6 for each of them. And this here is what we call as your probability distribution. And again, remember, this will be based on theoretical values because we didn't actually observe by rolling a single die, right? This is just what we are looking at. Like I said, think of it as theoretical, which is basically based off of your classical probability. Okay, and you can kind of read some of those details in there that they're talking about. So let's go ahead and take a look at our next example here, which this one is actually going to be based on observation, more of an empirical type of example rather than theoretical, right? So they're talking about a convenience store sells AA batteries in 2 per package, 4 per package, 6 per package, and 8 per package. Okay, so these are just individual packages of what size you get, right? So you can only get 2 batteries in a pack, 4 in a pack, 6 in a pack, or 8 in a pack. Now they are telling us the store sells 5 of these 2 packs, 10 of the 4 packs, 8 of the 6 packs, and 2 of the 8 packs over the weekend. So based on that, they're asking us to come up with a probability distribution. So your outcome is actually going to represent the package sizes. So you can get 2 per pack, right? 4, 6, or 8. And then how many did they sell will become your frequencies. So if you go ahead and add up your frequency column or row, that's going to add up to 25. So that's where they're getting this number 25 from. And then you calculate your probability. Remember, frequency is different, probability is different. So once you have calculated your total for the frequency column, then you're going to take each frequency for each individual outcome and divide it by the total, right? That's how we calculate probability. So you have what is the probability of selling 2 batteries per pack, and that's going to be 5 out of 25. Probability of selling 6 batteries per pack is 8 out of 25. And in that same way, we calculate for the 4 pack and the 8 pack, right? Now, once you have calculated your probabilities, then you can construct your probability distribution here. So that's again outcome X on the top. That's 2 batteries per pack, 4 batteries per pack, 6 batteries per pack, and 8 batteries per pack. And then using these frequencies we just calculated, for 2, it's going to be 0.20. For 4, of course, as you can see, it's 0.40. For the 6 pack, it's 0.32. And for the 8 pack, it's 0.08. Now, if you remember, we had talked about this before. Whenever we are talking about probabilities, and we talked about probabilities for our sample space, remember, they always have to add up to 1, which means all of these probability rows have to add up to 1. Or if you were thinking of this as being percents, then they need to add up to 100%, right? So that same thing is going to apply here in your probability distribution. So this is very, very important for us to remember when we're going through these probability distributions. The sum of the probability of all events in the sample space must equal 1. Your total should always equal 1. Also, for each individual event in your sample space, those probabilities can be between 0 and 1, or they can be equal to 0 and 1. So for each individual probability also, it can be a value between 0 and 1. They can also be 0, they can also be 1, but it cannot be anything outside of that. So you should not have probabilities more than 1. You should not have probabilities less than 0. And then, of course, your total probability for the sample space should also add up to 1. Okay? So, and you can kind of read some of those finer details in this paragraph over here. So the one thing you have to be careful about, your sum cannot be less than or greater than 1, okay, in your sample space, since the sample space includes all possible outcomes, okay. I've already talked about the sum, and then the second requirement where they were saying the probabilities can be anywhere from 0 to 1 as your values. The other thing you have to keep in mind, your probability cannot be a negative number, and your probability cannot be greater than 1. So this example here is basically just looking at, can we actually call these distributions probability distributions based on these two requirements. So the first thing you of course want to do is look at each individual probability and make sure it is between 0 and 1 or equal to 0 and 1, which this guy looks fine. And then when you add them, do they add up to a total of 1? Now if you add this up, this actually adds up to 1.1. So this guy is actually not a probability distribution because of course it's adding up to more than 1, right? For our part B example, you can of course see that this are all fractions, which are proper fractions. So that of course tells us that all of these values are going to be between 0 and 1. 1/4 is of course 0.25, 1/2 is 0.5, 1/8 will be 0.125. So all of those numbers are fine. Now when you add the total of your probability, does it add up to 1? So you can just plug those numbers in your calculator or do it by hand. It doesn't matter, but this will actually add up to 1.0, so it satisfies both requirements. So we can say yes, part B is a probability distribution. For part C, again, each individual probability is 1/4, which is 0.25. So that satisfies our probability requirement. And then when I add my probability row, 1/4 added into itself 4 times will also add up to a total of 1. So it satisfies our first requirement also. So again, we can say yes, C is a probability distribution. Now when you look at part D, you will notice that you have a negative probability in there, right? And you cannot have a negative probability. So just by having that negative number in there, we know this is not a probability distribution. And of course, when you add that up, you will see it does not add up to 1.0 anyways, but just being that negative also failed. So you can see our first one is not a probability because the sum of your probabilities is greater than 1. The second and the third one were both yes because they satisfied both our requirements. And the third one was a no because one of your probabilities is less than 0, or basically a negative number, right? So just a brief introduction into what probability distributions are, and we're looking into discrete random variables for these probability distributions. And of course you can see that these variables can be used in applications for business, education, engineering, and honestly a whole bunch of different other examples when we can do these probabilities. Okay, so let's take a look at a couple examples from our textbook over here. Okay, so we're looking at example 7 here from your textbook, and this one is just asking us to determine whether the distribution represents a probability distribution or not. So remember, as I said before, you cannot have numbers less than 0 or greater than 1 for each individual probability, right? They can either be 0 or 1 or anything in between. And also your total probability cannot add up to more than 1. So you can see right here in number 7 that we have this negative 0.8 probability for number 7. So that of course tells you that we cannot consider number 7 as a probability distribution, since our probabilities cannot be negative, right? So number 7 we would say is not a probability distribution. Okay, so now let's look at number 9 as our next example. So for number 9, again, you should see that each probability is 0.01, 0.1, 0.3, 0.3, 0.2, and 0.1, right? So each of those individual probabilities are between 0 and 1, so that's good. Now the question is, if we add all those 5 probabilities, do they add up to 1? So 0.1 and 0.3 is 0.4, then you have 0.6, 0.9, and 1.0. So yes, we can say number 9 is a probability distribution. Okay, so number 7 was not, and number 9 is. Okay, now the next example that I actually wanted us to look at is number 20 over here, and they're asking you to construct a probability distribution and draw the graph, but we're just doing construction of the probability distribution because you guys can do drawing the graph as practice, but I'm not going to be doing that right now in class. Okay, so we've got number 20, and here they're just asking us to construct a probability distribution, and they're saying the probabilities of a return on an investment of $5,000, $7,000, and $9,000 are 1/2, 3/8, and 1/8 respectively. So let's go ahead and see what a probability distribution for this would end up looking like. Okay, so this was number 20 from our textbook. So remember, your outcomes will go on the numerator, and our probabilities will go on the denominator. So our outcomes, they are telling us, is an investment of $5,000, $7,000, and $9,000, and then they told us each respective probability was 1/2, 3/8, and 1/8. So 1/2, 3/8, and 1/8. So of course you can see each one of those probabilities are going to be between 0 and 1, and then when we add our probability row, it's of course going to add up to 1, so you know it satisfies our probability requirements. Okay, and so this guy was number 20, and I will actually have a couple more examples for us to work through when we talk about this in class. Okay, so this was just our introduction to probability distributions. So if you have any questions, let me know, and I will see you guys in class. Have a wonderful day, guys. Bye-bye.